Okay, and welcome to the sixth part of section 4 from the M3 mechanics course. It's looking at motion in a circle where there's a possibility that a particle or an object will stop travelling in a circle. So in this situation we've got a particle moving in a circle, okay, and it's rotating around, but there's a chance that the particle will not reach the top of its circle, okay, where it may not have enough speed for the string in this situation to stay taut, to stay under tension. So I'll just let you read the question. So at this point, at the bottom of the circle, there's a tension, obviously. The tension here is mg, and if you also have to take into account the centripetal force, the tension is equal to mv squared over r, the centripetal force, plus the tension required to keep it moving upwards. Okay. Now then, that's obviously only valid at this point. As it swings round, you start to bring in a trig function for the weight component that the tension is trying to hold. So as the initial kinetic energy is half mv squared, you could say that if you take this root 3gl for v squared, okay, you can square that and then you get 3gl. You set that equal to half m 3gl is equal to the gravitational potential energy plus the kinetic energy. You can cancel all the common terms of m out here. So 3gl is equal to 2gh plus v squared. Okay, just a rearranging of this. So this is an expression formed from the total energy. Now, as the string raises, or as the particle rises, you're going to be gaining some potential energy, but the velocity is going to be decreasing. Okay, so this is going to remain as a constant. So the height, of course, is going to decrease. Okay, so I've got a height here, okay, but it's raising upwards. So this distance here is L cos theta, okay, with this is L, this is theta, so this is L cos theta. So the height is the length of this, take away that, okay, so that gives us this height here. So L minus L cos theta, or that can be factorized and you can take the common L out. So that gives us a little idea of what we can, an expression that we can write for the height, which is what we can use for the gravitational potential energy. And then we can look at v squared again. So the tension goes back to the original of tension is equal to this. Okay, so we substitute this in here, and then we just need to tidy things up a little bit. So in tidying it up, we get a nice little formula that's being slowly simplified. So we get a value for the tension. Now, how do we get that value for the tension? First, basic principles. Centripetal force is going to be dependent on velocity. Velocity is going to vary due to the total potential energy remaining constant. And there we go, that's it. So, find the height of P above A at the instant when the string goes slack. So the string will go slack when the tension is equal to 0. okay, when there's no tension in the string. So at a certain height, the velocity from the centripetal acceleration just isn't going to be enough to keep a tight string. So the point where tension equals to 0 is this. So that's very easy. We simply move this mg to the other side of the equation, and then we can cancel some things very, very easily. Okay, so if we cancel the common mg, we're just left with the 1 here. We divide through by 3, we get minus a third. It's equal to cos theta, so theta is cos to the minus 1 of minus a third. Okay, so then we can say what the height is. So taking that value for theta, we then have a height, and at that point this is our final answer. So if we move on to question C, part C, find the maximum height above A reached by P before it starts to fall to the ground again. So C, find the maximum height above A. So A is this point in equilibrium, okay, at the bottom here. So you've got O to A. So how high does it go? So you're going to need to use L here. So if you take all of this, okay, you've got this horizontal velocity. Now you've got your kinetic energy is going to go to increasing the gravitational potential energy, so it's going to go upwards and upwards and upwards. Now at a certain point, when the string goes slack, you will lose some gravitational potential energy. So when the kinetic energy goes to a certain value, the gravitational potential energy must have gained that value. So by keeping those at a constant, mgh is equal to half of the kinetic energy. Okay, so we have that here. Now when we look at the height of that, we've got this little height equation here, and continuing, we get a nice final answer of 40L over 27. Okay, so this is our final answer for the height reached. So that's just a extension of all of this, okay, or a multiplying out of all of this. So you had a term for the height, and then it's done. Okay. Obviously, you need to take care with my handwriting here. Okay, we've got some L's here. So look after those L's. We've got an L here. So that is that. Okay, so a nice simple example to start you off when the particle may not stay moving in a circle due to not having enough velocity. And that goes back to the original postulates from the previous section of the course, where you might have a particle moving in a circle, but it might not have enough velocity to reach the top of the circle. Okay, so I hope this has helped, and if not, have another look, see if you can follow what I'm doing, and possibly look over 4.5 of the course, as well as any other work from 4.6.